It's a train as fast as a plane. This is maglev, a revolutionary transportation system.
Yeah, maglev is not rocket science.
But something's gone wrong. In the world's first crash of a magnetic levitation vehicle, 23 people die. This is the story behind the future of transport. Deep in the pastoral countryside of northern Germany lies a facility that's developed a magnetic levitation vehicle, or maglev. The Transrapid test facility cost over $1 billion and was built to put the magnetic levitation vehicle through its paces. This demonstration track has been in operation for more than 20 years, and the maglev has traveled nearly 1 million kilometers on it. The test track is open to the public, and each year it attracts thousands of tourists eager to experience the thrill of riding a magnetic levitation vehicle themselves. In total, more than 500,000 curious visitors have experienced high-speed levitation without incident. But one September day, the maglev faced a shocking turn of events. It set out for a test run and quickly accelerated to 200 kilometers per hour. It usually blazed around the 31.5-kilometer test track in minutes, hitting speeds of 450 kilometers per hour on the straightaways. But less than 60 seconds after it started this test run, the unthinkable happened. A maintenance vehicle was also on the track, checking the guideway for debris and problems. It was the first major accident for a technology that had been a century in the making. An investigation got underway. Questions were asked about what had happened and why. And there was a great deal at stake, because maglev was on the verge of a breakthrough. It was ready to change the way we travel in the 21st century, just as the aeroplane did in the last. Maglev is a magnetically propelled vehicle that floats above a guideway and can travel at speeds of more than 500 kilometers per hour without really leaving the ground. And it's driverless. Most people haven't heard of it, but according to these experts, future generations will head to the maglev station instead of the airport. If what they say is true, maglev is in a transportation league of its own. It offers the possibility of inter-urban commuting at speeds faster than a Formula One race car. With maglev, the speed of an aircraft meets the convenience of a train, offering fast loading and unloading at stations located right in the heart of town. Kevin Coates is a transportation consultant.
It's phenomenal. So you can actually plan your trip. Imagine this, traveling around the United States and moving from city to city, typically for trips 500 miles or less, moving from city to city and being on time to the second on every trip. People that travel around this country, I think, would find that unbelievable, but that's what this new transportation system promises.
The maglev's levitation system is what separates it from all other forms of mass transportation. This technology represents a radical approach to locomotion. The maglev floats over a guideway, and the guideway and the vehicle work together to create and control magnetic levitation and propulsion. Neither part is compatible with any other transportation system. Transrapid uses magnetic attraction. Along the length of the vehicle, magnets attached to the top of this cast aluminium support arm are pulled towards the bottom of the guideway. Computers regulate the power to the magnets and keep the vehicle suspended at a height of precisely 10 millimeters. Whatever load it's carrying, the maglev will never make contact with the concrete and steel surface of the superstructure. Each maglev vehicle weighs 50 tons and is able to carry a further 20 tons of cargo, making it heavier than a tank. And this sophisticated levitation system not only lifts and then suspends 70 tons of vehicle and cargo, it also propels it at speeds of more than 400 kilometers per hour, always 10 millimeters above the guideway. It sounds incredible. But here, at the Transrapid test facility in Germany, a team of engineers is already developing the next generation of maglevs. This is the largest test facility of its kind in the world. The maglev vehicles are assembled at a plant near the test track. Each component is custom-made to exacting specifications. Heiko Lobach, who's working on the TR09 engineering team, wants to change the way we travel.
We have a lot of misunderstandings. We'll have much lower noise. We will have less energy consumption. We will also have no emission from gas or from also not from the magnetics, because the magnetic field of the levitation and guidance magnets is less than the magnetic field from your television at home.
Its developers have such faith in this machine that they've sunk billions of dollars into it. So who's buying the maglev system? A long way from Germany and the People's Republic of China, maglev is revolutionizing the transportation infrastructure. China is quickly emerging as an economic powerhouse, and it's decided to start building magnetic levitation systems. Leaders here can see a lot of benefits. The nation has a population of 1.3 billion people, and they need to find an efficient way to move both people and products in the shadow of a looming fossil fuel shortage. They're planning for the future, and that plan includes maglev. They first ordered a 30-kilometer maglev system to run from downtown Shanghai to its international airport at a cost of $1.2 billion. But the Transrapid engineers knew that this first contract was really an audition. The government here was also planning additional lines and wanted to expand maglevs throughout China. Prospective maglev lines included one between Shanghai and the tourist town of Hangzhou, a 170-kilometer line with a budget of $4 billion, and a connection between Shanghai and Beijing, over 1,200 kilometers, with a price tag of $22 billion. That's the equivalent of $18 million per kilometer. So why did the Chinese buyers decide to invest in this technology when there were already so many planes and high-speed trains? And why would they bank the future of their economy on a prototype? For the engineers at Transrapid, the answer to this is simple. There's a major problem with the world's transportation system. According to them, cars, trains and planes have had their day. And the airline industry in particular is facing a looming crisis. People love jets because they're fast, convenient and have reduced the time required for long-distance travel. But the demand for air travel is increasing. On the ground, delays are a major problem, and now the skies are also facing winged gridlock. Every year, more aircraft are being built, along with larger airports to service them. And with the introduction of the Airbus Super Jumbo A380, we're also building bigger and bigger planes. But this solution does nothing to address the other major problem facing airlines: skyrocketing fuel costs. A 747 burns 170 liters a minute, enough fuel to fill 3 cars every 60 seconds. And that, according to the maglev experts, is creating a problem.
And as oil gets more expensive, and it will, as it becomes more rare and more people are demanding it, the cost of flying is going to increase. There's no way around it.
And if that's the case, people are going to look elsewhere for a viable transportation system that can replace air travel. Transrapid charged its engineers with finding the Achilles heel of the airline industry. It discovered that the weakness is the short-haul flight of under 700 kilometers. In the US, flights of less than 1,000 kilometers make up about 50% of the airline market. They're costly, inefficient, and plug the skies with aircraft. So Transrapid designed its maglev system to break the airline industry's grip on these short-haul routes and replace them with a fast, environmentally friendly and cost-effective solution. And China was the first customer. The Chinese government recognized the potential of maglev and ordered the first commercial magnetic levitation system in the world. But then it had to be built, and that's where the problems began. Just like the research phases of the aeroplane, car, train, and spacecraft, the maglev was in development for decades. Railroads in Germany had a long history of innovation dating back to 1835. Trains there were traveling at over 200 kilometers per hour in the 1930s.
A scale model is displayed on a mile-long test track, hitting speeds up to 93 miles an hour, taking the 45-degree turns without a shudder.
It was in the 1930s that German inventor Hermann Kemper first dreamed of a train without wheels, a system that would harness the power of magnets to both lift and propel vehicles forward. But two major problems slowed down its production. The first was the power of computers. Powerful electronic components such as computers were necessary to control the system, so it would be decades before the theories could be tested. These weird-looking manifestations didn't go very fast compared with today's maglevs, but they were crowd pleasers, and enough to keep the development lurching slowly ahead. But as the speed of the vehicles increased, a second problem surfaced. The engineers hadn't found a levitation system that was stable or reliable enough to lift the sleds off the ground. They were moving forwards by magnetic propulsion, but frustratingly still dependent on wheels. Because they couldn't get the vehicles to levitate, research and development of this radical technology was in danger of being shut down. Maglev was on its way to becoming just another footnote in the history of failed experiments. But then something changed that got the maglev project off the ground. In 1974, Transrapid engineers tried out a new system, splitting the motor in two. They mounted the magnets on the sled and installed the primary motor in the track. This reduced the weight of the vehicle. With help from rockets, this prototype was propelled forward at 401 kilometers per hour. It was the breakthrough they needed to breathe new life into the project. Now, Transrapid had just one thing left to do to convince the world that this could be a great system. It had to build one. With the computer and motor problem solved, it began to build a system for human cargo. In 1980, it chose the Emsland region of northern Germany for its first permanent test track, a 31.5-kilometer double-loop configuration. Far away from prying eyes and critics, it then set out to prove that the technology it had developed was revolutionary. The guideway system was built to resemble a commercial track in both size and distance. With this in place, engineers could push the maglev to the limits of speed, endurance, and handling. Today, Transrapid is on its 8th version, the TR-08. It finally succeeded in building a stable levitation system, and by operating the train on a day-to-day basis, mimicking the operation of a public system, researchers now believe it will redefine our notion of distance travel. The maglev system combines the technology of conventional rail and the time advantage of air travel, making for an energy-efficient and low-maintenance, high-speed ground transportation. But many countries, including the United States and much of Europe, continue to shun the system. Critics suggest that maglev is too much of an untested system to build from scratch. In America, high-speed trains are almost non-existent, and plans for their introduction remain in limbo. Kevin Coates is frustrated by the lack of interest in maglev.
All these guys are rail guys, and they don't want to go with something new that they don't understand, and that's a problem. And all these consulting engineers that are out there, trying to advise government agencies what to do are going with what they know. And they don't know maglev. They know rail. They know light rail. Well, light rail is a fancy name for trolleys. We've already been down the road with trolleys.
But in China, people understand the need to move beyond regular rail transportation, which is considered an outdated system. Indeed, what got the Chinese government really interested in the maglev was the incredible future potential of the technology. They knew that if it worked, it could change transportation throughout China. And what better place to test the first commercial track than the city of Shanghai? This bustling metropolis is home to 20 million people. It's a place where old China is being swept aside and a new, modern China is emerging from the rubble. The Chinese are building the city of the future here, and they want to set the standard. Business professionals are attracted to Shanghai because of its modern environment and new job opportunities. And that can create problems on the streets. Previous predictions indicated that more than 2 million vehicles would clog the streets in the coming years, and new highways were becoming overrun as soon as they were built.
The reason the Chinese decided not to go with airports or highway systems, they realized that moving people between cities using electricity is a sustainable solution for their future transportation needs.
In March 2001, construction began on a high-speed connection between Shanghai and Pudong International Airport, the first step toward building a transportation infrastructure for this modern economy. A trip that took an hour in a car in congested traffic producing noise and pollution could potentially take 7.5 minutes on a maglev line gate to gate. Using maglev to help solve their transportation problems seemed like a great idea, but there were immense challenges ahead. It had never been done before. The German engineers would have to build a radical transportation system and build it right the first time. And they'd have to deal with the sinking ground under Shanghai. Over the last century, it's sunk by more than 2 meters, and there's no end in sight. The job of building the guideway system was given to Chinese engineers. They began to build the monster motor that would stretch from downtown Shanghai to its international airport. The first phase of this mega project was to clear the route. They had to pull down buildings and move people who lived along the way. But the real problems began when they looked at the soil underneath those homes. The entire route sat on the floodplains of the Yangtze and Hengpu rivers. Silt and sand had been deposited there over millions of years, and the soft, unstable ground wouldn't support the massive infrastructure needed for the maglev. Carlos Ventura is a structural engineer.
Load-bearing soil, like in places like in Shanghai, is a soil which has very low capacity to resist overburden pressures or loads that are going to be put on top of it. And that will eventually have a detrimental effect on the structure because the structure will sink or top over or have excessive deformations that are not acceptable.
China has been hit by devastating earthquakes in the past. Should an earthquake strike Shanghai, the soil conditions there could result in a process known as liquefaction, or liquid soil. In this simple experiment, Professor Dawn Shuttle from the University of British Columbia demonstrates how liquefaction can topple an unsupported structure.
When the earthquake happens, the particles of sand try to move into a denser configuration, but because the water's in the way, the load is instantaneously transferred to the water rather than the soil, and the building will sink.
A proper substructure, like pilings, will prevent a structure from collapsing. But the problem facing engineers here was precisely how much substructure to build. To keep the guideway from settling and to minimize the impact of any future earthquakes, the engineers came up with a plan. The idea was to distribute the enormous weight of the guideway deep down into the earth. The guideway sections would be mounted on a series of piers positioned every 25 meters along the route. Each pier would rest on a pile cap, a reinforced block of concrete sitting just below the surface. And supporting the foundation would be the piles themselves. The engineers had to take two things into consideration when building the caps. First, the bigger the piers, the bigger the foundations would need to be. In Shanghai, the pile caps were 2 meters deep and 10 to 12 meters wide. This meant that along the route, there could be as little as 1 meter between the caps. But the engineers also needed to take into account the load-bearing capacity of the soil in which they were building. The worse the soil, the more piles they'd need and the deeper they'd have to go. In Shanghai, the soil was so bad that the engineers had to drive the piles down to 30 meters. In some cases, they had to go as deep as 70 meters, the equivalent of a 23-story building. And each pile cap covered 20 to 24 individual piles. Over the course of the project, they sank over 24,000 pilings. They had just 16 months to complete this phase before the first magnetic levitation vehicles arrived from Germany. Meanwhile, the Transrapid engineers were under pressure to deliver the vehicles that would travel the Chinese-built guideways. They'd never built a commercial maglev system before. They'd only ever delivered prototypes. But this wasn't a trial product. The Chinese needed it to work, and work flawlessly. Having landed the billion-dollar Shanghai maglev project, they had just 22 months to deliver. The plan called for taking the TR-08 prototype to large-scale production. The passenger compartment presented few challenges, because this section was built like any other passenger train compartment. But that's where the comparison ended. Unlike a typical train, which has one locomotive pulling many cars, the entire maglev is a propulsion and levitation unit. For Shanghai, the pressure was on to build 15 distinct propulsion systems on a nearly impossible schedule. A maglev has virtually no moving parts and no generators to provide power to the lights, computers, and electronics housed in the carriage. Once it's underway, it draws power from the grid to activate the magnets. Giant batteries store energy to supply the lights and power the onboard computers during operation. They also act as a backup for the magnets. In the event of a power failure, the maglev won't drop suddenly to the guideway, because the batteries will kick in and hold it up for long enough so that it can be brought to a smooth stop. The propulsion and levitation system uses electromagnets. Coiled wire is pumped with electricity to generate a magnetic field, and the more coils and current, the more powerful the field. How many magnets are on board and how much each one can lift are trade secrets. But by controlling their energy, Transrapid uncovered the key to lifting and propelling their 70-ton vehicle. The linear motor used in the maglev magnetic propulsion system can be found in other types of transport. A linear motor is used whenever fast, stable acceleration is required, and sometimes that means fun and games. At this amusement park, magnetic propulsion technology adapted from maglev is used to propel this sled and its riders at high speeds. The object of the exercise is to give customers a taste of the G-forces that magnetic technology can offer. It's one of the fastest rides in the United States. Passengers are blasted from 0 to 160 kilometers per hour in just 7 seconds. They rocket up a 41-story tower, stop and hang for 6.5 seconds in complete weightlessness as the sled comes to a stop, and then begin the terrifying backwards descent. This is the kind of takeoff the maglev can achieve. But it's still only a fraction of its potential acceleration power. The Navy is adapting maglev propulsion for their catapults on board aircraft carriers. They currently rely on steam-driven pistons to launch aircraft. This is tried and true, but it's also antiquated, energy inefficient, and above all, bone-jarring, both for the pilots and the planes. Future aircraft carriers will be equipped with maglev propulsion systems for launching and even landing aircraft using super magnets. The advantage is greater control and longer aircraft life. And that means control over how much power to apply according to the weight of the aircraft. Given the opportunity to unleash its full potential, the results are spectacular. At the Holloman Air Force Base in the New Mexico desert, there's a test track which uses a rocket-propelled sled to test weapon systems up to Mach 8. In 2003, these rocket sleds set the land speed record at 10,430 kilometers an hour.
1, 0, fire.
It's this powerful combination of rockets and magnets that takes maglev to hypervelocity. With speeds like that, a maglev vehicle moving through a vacuum tube or tunnel where there's no air friction could reach more than 6,000 kilometers per hour. To really appreciate this amazing machine, you have to ride it. And at the test track in Emsland, the public gets to experience a maglev vehicle firsthand. This is the Transrapid Command Center for the maglev test track in Germany.
We have a 32-kilometer long guideway here with about 8 kilometers of straight track for high-speed testing, and in the northern part and the southern part of the test track we have a loop. And by this configuration, it's also possible to perform duration test rides with the vehicle.
After careful inspection in the hangar, the command center gives the green light and the maglev is ready for its high-speed test run. With the click of a mouse, the computers activate the magnets and the maglev begins to defy gravity. This thoroughbred train is now ready to stretch its legs. Today, it'll hit a cruising speed of 400 kilometers an hour. With the technicians in place, the speed test begins. These men and women are the only human parts of an entirely computer-controlled operation. Transrapid believes that by taking humans out of the operation equation, it has a smarter, safer system, so it's handed control over to computers.
Top speed of the Transrapid's 310 miles per hour or 500 kilometers per hour. You know, at those speeds, human beings can't react fast enough. They're used to keep the vehicle the exact distance from the guideway so that you get a smooth ride, and then computers are also controlling the power that's delivered to the vehicle from the track to propel it.
At this full-scale test facility, every run has a purpose: to further the technology. The maglev is fully automatic, so computers control the acceleration. It's strong and steady, but gradual enough that passengers are not thrown back in their seats.
First time I rode the maglev was in Germany at the test track, and I was in the lead carriage and looking out the window. And what's really amazing about that experience is that as the vehicle moves down the track, you almost feel like you're looking at a video animation of something. It's so smooth. There's really, it seems unreal that anything moving that fast could actually be that smooth. And the reality is that the precision between the vehicles and the guideway is so exact that vibration is it's cut to an absolute minimum.
But there's no time for the technicians to take in the scenery. They're entirely absorbed in the test run. They round the giant loop and prepare to accelerate over the 10-kilometer straight stretch. The maglev will run up to its maximum speed on this test. Because the maglev vehicle levitates, the friction from wheel-on-track contact found in conventional trains is eliminated. This means higher speeds and faster rates of acceleration and deceleration. Power is measured not in horses, but in bytes and kilowatts. These supercomputers make millions of calculations per second, sending and receiving information from the magnets and the guideway to keep the maglev stable and moving forward.
It's sort of like a surfboard riding on a wave, a magnetic wave, and that's how it's propelled. And how the engineers propel the Transrapid is by speeding up the wave in the guideway. It's very controlled, and you can walk around without a seatbelt. It's all very smooth.
The test facility is able to simulate every situation the maglev could conceivably face during commercial operation. It's been run through rain, snow, wind, and even lightning storms. The speed in the curves is restricted to 200 kilometers per hour for the sake of passenger comfort. On the test track, as in normal operations, riders can't be subject to higher centrifugal forces. As it hits the straight stretch, the maglev accelerates to full speed. This footage was shot in real time. The technicians gather data for analysis, and the speed and performance of the maglev is carefully watched back at the command center. It hits 400 kilometers per hour as it blazes down the straightaway. The maglev successfully completes the test run. The data is collected, and then the engineers go back to the drawing board to work on the next generation of maglevs.
Working here in this team is really very interesting, but no working day is the same as a day before. We have so much different tests to do, and that makes it very interesting. And for sure, now we are in a phase where the system goes into commercial operation, and this makes it still more interesting as before.
The world's first maglev was delivered to Shanghai in the summer of 2002, and the heavy lifting began. Any failure could be measured in fractions of a millimeter. Workers began the delicate operation of picking up the passenger compartment. It was a matter of only a few months since they'd started to build the maglev, and careful watch was kept on every step as the chassis and the passenger compartment were put together. The computers were mounted. Then it was time for the moment of truth. When they applied power, would it lift off? Switches were thrown and the carriage began to levitate. After the successful test, it was pulled apart. The upper chassis separated from the propulsion system. The carriage sections were then loaded onto flatbeds and taken to a cargo ship for the journey to Shanghai. But two problems remained. Transrapid had managed to make 3 cars in 15 months, but it had to deliver 12 more over the following 12 months. And would these carriages assembled so carefully in Germany work on the guideway constructed in Shanghai? The results had the potential to be the biggest thing since the locomotive, or a billion-dollar disaster. On the 11th of September 2002, a mere 18 months after the start of construction, the maglev carriages were mounted on the guideways, and the trial run began. This was a necessary step before the public could ride the maglev from downtown to the airport. With the pomp and ceremony behind them, it was now time for the engineers to prove that the concept worked. The German and Chinese construction teams came from different engineering traditions and systems. Would they have managed to overcome the problems of time and distance and execute design specs with system tolerances of less than 2 millimeters? The guideways in Shanghai were an adaptation of the German engineered version. Instead of building a 50-meter-long guideway beam, the Chinese engineers cut that in half and used 25-meter girders instead. This doubled the work and the number of guideway beams required for the 30-kilometer stretch, but it made it easier to transport and assemble the spans, and meant that the Chinese team was able to meet the construction deadline. Even for the experts, this was a technical marvel.
In Shanghai, you've got a 19-mile-long guideway system that is built to within 1 millimeter tolerance through its entire length. And to my knowledge, there's nothing in the world that comes as close to that level of precision.
To keep the guideway within the strict operating specifications, engineers used an adjustable bearing system which allowed them to correct the guideways if they settled. The 3-way bearing system raised or lowered the guideway beam to adjust for settling. There were more than 10,000 adjustable bearings along the entire route. But not all the guideway sections were rigid pieces of concrete. Some were made of steel. These steel switches could be bent on command, allowing the train to change guideways. But the speed was limited to 200 kilometers per hour in the curves. The problem was the human passengers. A sudden change in direction at high speed would throw passengers around. With the guideway virtually perfect and the first maglev vehicle safely mounted, a test run was performed with a single train. In the speed trials, engineers got it up to 501 kilometers an hour and established a new world record for commercial rail systems. But they had one more hurdle to face. There were 2 guideways running side by side. They now had to run 2 vehicles past each other. The trains would pass in close proximity at a combined speed of 860 kilometers per hour. Based on simulations and research, the vehicles were designed and built to survive high-pressure wind effects as they passed each other at full speed. But an actual passing test had never been done before. The engineers couldn't sign off for public use until this test was completed. One left from the Longyang Road station downtown and the other from the Shanghai Airport station. In just over 3.5 minutes, they'd reached the halfway point on the line where the vehicles would pass. Each accelerated to a top velocity of 430 kilometers an hour and would sustain this velocity for less than a minute. At a combined speed of 860 kilometers an hour, the maglevs passed each other. It was a major success for the team. The maglevs survived this critical trial run intact. Now just one question remained: would people pay to use it? The Chinese flocked to this new system, and within 3 years, 8 million passengers had ridden the Shanghai maglev.
It's truly a phenomenal transportation mode, and it's the reliability aspect of it that I'm most impressed with. It's 19 miles apart. The trip's about 7 minutes and 30 seconds. But the vehicles leave and arrive on time to the second 99.92% of the time. That's phenomenal. I mean, that's almost too perfect. People aren't going to